Okay, this was the slide we left off on. The MMC modifier is applied in the feature control frame. After the tolerance value, the MMC modifier indicates that the tolerance applies when the hole is at its maximum material condition. That is the smallest hole. As the size of the produced hole is above the maximum material condition, more positional tolerance is allowed. The whole idea there is if it fits at the maximum material condition, it will fit even better as the part deviates from the maximum material condition. So essentially you get more position tolerance as the hole deviates from the maximum material condition. These are typically used for clearance hole applications. If the hole is larger than MMC, it can be off the true location by more and still fit in the next assembly. Here's some cartoons of what that means. Here we have a position tolerance for a hole with the MMC modifier. I have 25 thousandths allowable position at the MMC, but then as my hole varies up to the least material condition, I add tolerance. For every thousandth the hole deviates from MMC, I pick up another 1,000th of true position tolerance. So at our least material condition, I have 35 thousandths allowable position tolerance. Okay, so what that means is that as the hole gets bigger, I get more tolerance. Okay, the effect of least material condition. The least material condition modifier is applied in the feature control frame after the tolerance value again. The least material condition modifier indicates that the tolerance applies when the hole is at its least material condition. As the size of the hole, produced hole, is below the LMC condition, more positional tolerance is allowed. And then typically this is used for applications where edge distance considerations are of a big concern, but not typically. MMC is used a lot more than least material condition. Here's the example of least material condition modifier. Here we have the hole produced at MMC, in which case we get 35 thousandths allowable tolerance. But when the part is produced at the least material condition, we only get 25. So it's kind of like MMC, only backwards. Proof of MMC concept. This is one of your objectives. Number 4, provide examples that prove the validity of the MMC concept as it applies to positional tolerance. I guess what we're saying here is that, we have these two plates shown. We have a plate with pins, and then we have a plate with clearance holes. We have a small clearance hole, snug fit on the one pin, and then we have a large clearance hole and a loose fit on the other pin. Now, the larger holes provide more clearance, therefore more positional tolerance can be provided while still assuring the fit. Okay, so what we've done here is we've produced this hole at a bigger size here. We have more clearance. So as we have more clearance, we have more room for this pin to be off location. So that essentially proves the MMC concept. So for every thousandth you deviate from the maximum material condition when you're using the MMC modifier, you get another thousandths positional tolerance. And that is done because as the hole deviates from MMC, you pick up more clearance. You pick up more clearance, you can use that clearance for positional tolerance. Okay, so I want to bring up a concept of fixed versus floating fastener. We're just going to talk about this conceptually. So in a floating fastener condition, what we have is we have two members here that are going to be bolted together using a through bolt and a nut. When we call that floating, what happens is the fastener is passed through multiple clearance holes and is fastened with a nut. Whereas you have a fixed fastener over here, one member has fixed the fastener. In this case, it's a threaded hole, but that could also be a press fit, etc. Okay, so floating fastener. Fastener passed through multiple clearance holes, Common to use the same size clearance hole for all parts, but it's really not required. But with a fixed fastener, the fastener passes through multiple holes, but one of those fixed fastener locations via threads, a press fit, or a taper. Okay, so the part is fixed to one, and the part is clear to the other one. That is a fixed fastener. We're not going to talk much more about that. Additional tolerance for position specified to apply at MMC. Tolerance value shown only applies at MMC. As the size moves away from MMC, the allowable position tolerance increases. The tolerance zone increase is directly related to the departure from MMC. So let's talk about an example for that. Okay, in this case we have a hole with a tolerance specified at MMC, a positional tolerance. Okay, in this example, our part was produced at 503 thousandths. Okay, so therefore, if our produced part is 503 and our specified MMC is 500, we get 3 thousandths bonus tolerance. Okay, so what is our overall tolerance? Our overall tolerance is going to be the specified tolerance, which is this 35 thousandths, plus this bonus tolerance we picked up, 3 thousandths, which gives us an allowable tolerance of 38 thousandths. Another way to look at this is looking at the produced size, which is 503, minus the virtual condition. The virtual condition would be the smallest hole, 500, minus 0.035, so 0.465. So therefore, our allowable tolerance is 38 thousandths. So two ways to look at this. As virtual condition or as bonus tolerance, but either way gets us the net result of, yes, we are 3 thousandths over our MMC, so therefore we get 3 thousandths more positional tolerance because our part tolerance is specified at MMC. Okay, let's do the same example except for a shaft. In this case we have a shaft of plus 4 thousandths minus nothing with 28 thousandths at MMC position tolerance. So we're going to produce this part at 379, which is, well, we're going to produce this part at 376. 379 is the MMC size. 376 is the produced size. So therefore, if we subtract the produced size from the MMC size, we get 3 thousandths. We have our specified tolerance of 28 thousandths. We add to that our bonus tolerance of 3, and we get 31. The other way to look at it would be to take our virtual condition, which is 407, which becomes our maximum material condition, plus this positional tolerance, and then 407 minus the 376, which is our produced size, gives us an allowable tolerance of 031. So for every thousandths we deviate from the maximum material condition, we pick up another thousandths tolerance. Okay, here's another topic: advantages of position tolerances over coordinate tolerances. This is objective number 8. Position tolerance gives us a clear definition of the requirements. There really is no standard defining coordinate tolerances. We get an increased tolerance zone area with positional tolerances. And then when we're using MMC, we get an additional bonus tolerance that's available. Okay, so coordinate tolerance is typically shown right here. If you're locating parts by just a tolerance, you put a dimension on a drawing, not a basic dimension. You put a tolerance dimension on a drawing for a location of a hole. What you'll end up with is a square or rectangular tolerance zone. So for instance, this one would be plus or minus 7.5 thousandths. Okay, and so this square zone, it really isn't I'm going to call it equitable. Okay, so what happens is, like we're depicting here, we have this one point out in the corner, and we're calling that's accepting. Okay, but we got this other point is being rejected, but it's the same distance away from your true position. Okay, so that is one of the advantages of using positional tolerances. You pick up the extra area, increased tolerance zone area. You pick up these little pieces of the circle around there. That's one of the things that is an advantage. Here's the big one, as I see it, and we'll talk about this. We'll talk about this in the next movie. Thank you.